In 1997, a mechanical convoy arrived at the gates of a protected national park in northwestern Costa Rica. It was a fleet of 1,000 heavy dump trucks, and over the course of several months, they proceeded to commit what looked like an environmental disaster. They drove into the conservation area, backed up to the edge of a degraded rocky pasture, and unloaded 12,000 metric tons of industrial sludge. This wasn't clean landfill. It was a neon orange slurry of peels, pulp, and seeds. It was wet, heavy, and rotting. In the intense tropical heat, the pile generated a stench so powerful it could be smelled for miles downwind. It attracted clouds of flies so thick they looked like smoke. To the local residents and the watching public, this did not look like conservation. It looked like pollution. It appeared to be a massive corporation using a nature reserve as a cheap, illegal landfill to get rid of their garbage. The optics were terrible, and the backlash was immediate. But 16 years later, when a team of researchers from Princeton University returned to the specific coordinates of this crime scene, they didn't find a toxic wasteland. They found a biological anomaly that defied their maps. The pollution hadn't killed the forest. It had terraformed it. To understand why anyone would dump 12,000 tons of agricultural waste onto a national park, you first have to understand the broken machine that is the tropical dry forest. When we think of the tropics, we usually picture the rainforest, wet, evergreen, and resilient. But the tropical dry forest is a completely different engineering challenge. It faces a brutal 6-month dry season where the moisture effectively vanishes from the air and soil. Today, less than 2% of this original ecosystem remains intact across Mesoamerica. It is one of the most threatened biomes on the planet, not just because of chainsaws, but because of a specific biological weapon introduced by humans: African pasture grass. The specific antagonist in this landscape is a species called Hyparrhenia rufa, Jaragua grass. It was imported to the Americas for cattle grazing because it is functionally indestructible. It is what botanists call a C4 grass, which means it is evolutionarily adapted to handle high solar radiation and extreme drought without dying. But its most dangerous feature is that it is pyrogenic. It loves fire. This grass creates a feedback loop that locks the land in a state of permanent death. In the rainy season, it grows aggressive and tall, reaching heights of 2 meters. But when the dry season hits, it dries out completely. It turns into standing tinder. When a fire starts, whether from a lightning strike or a rancher clearing land nearby, the grass burns with intense, rapid heat. This thermal shock acts as a filter. The native woody seedlings, the baby trees that would eventually form a forest, are incinerated instantly. They lack the root reserves to survive the blaze. But the invasive grass is different. Its root systems are deep and insulated underground, and they survive the fire perfectly intact. When the rains return, the grass sprouts up faster than anything else, stealing the sunlight and sucking up all the available nitrogen in the soil. This stops the trees from ever establishing a foothold. It creates a stable state of degradation known as the green desert. It looks lush in the rainy season, but it is biologically simple and broken. These lands will remain pastures for centuries because the forest cannot fight its way back through the grass. For the engineers at the Área de Conservación Guanacaste, this presented a nightmare scenario. The traditional solution to this is active restoration. You plant trees by hand, you water them, and you suppress fires. But in a landscape dominated by Jaragua grass, active restoration is a financial black hole. The grass grows so fast that you have to manually cut it around every single seedling, every single month, for years. If you miss a few weeks, the grass chokes the tree and your investment dies. To restore tens of thousands of hectares would require millions of dollars and an army of laborers that simply did not exist. They did not need a gardener. They needed a way to break the mechanical advantage of the grass without spending a fortune. The solution came from a convergence of waste and want. Just north of the park boundaries sat the Del Oro fruit processing plant. As a major producer of orange juice concentrate, the factory was generating massive quantities of organic waste every single day. They had mountains of peels, pulp, and seeds. This waste was a significant economic liability. Citrus waste is highly acidic and sucks oxygen out of the water. If you dump it in a river, it kills the fish. If you put it in a landfill, it leaches acid and generates methane. Del Oro was looking at a multi-million-dollar expense to build a dehydration plant to turn the peels into cattle feed just to get rid of them. Daniel Jansen and Winnie Hallwalks, two ecologists advising the park, saw an opportunity for industrial symbiosis. The park had a deficit of organic nutrient capital. The factory had a surplus. They proposed a radical trade. Del Oro would donate 1,200 hectares of its own forested land to the park. In exchange, the park would provide biodegradation services. The factory could dump its peels on the degraded pasture land for free. The hypothesis was elegant but brutal. Jansen believed that if you applied a massive enough layer of organic matter, you could smother the invasive grass and recharge the soil in a single stroke. So, the trucks began to roll. The scale of this job was massive. They did not just sprinkle the peels, they layered them. 12,000 metric tons were spread across a 3-hectare plot. The sludge was piled to a depth of up to half a meter. That is roughly 400 kilograms of wet biomass per square meter of soil. This massive input triggered a 3-phase chain reaction that completely reset the ecological clock. Phase 1 was mechanical suppression. Hyperrhenia rufa is a heliophyte. It requires full sunlight to make energy. When the trucks dumped a 2-foot layer of wet, heavy sludge on top of it, the grass was instantly plunged into total darkness. The sheer weight of the peels compacted the soil, and the initial fermentation consumed all the oxygen at the soil surface. The immortal grass roots were crushed, starved of light, and suffocated in an airless environment. Within weeks, the invasive species was dead. Phase 2 was the larval bioreactor. Critics at the time predicted that the peels would simply dry out and mummify, or poison the land with acidity. They failed to account for the power of the tropical insect community. The site became a massive open-air bioreactor. Millions of fly larvae colonized the piles. To a casual observer, this was a disgusting, writhing mess. To an engineer, it was a processing plant. These larvae performed 2 critical functions. First, by tunneling incessantly through the wet pulp, they acted as microscopic aeration units. They introduced oxygen into the pile, preventing it from becoming a septic swamp. Second, they consumed the complex carbohydrates in the citrus rind and converted them into frass, insect manure. They effectively pre-digested the nutrients, breaking down the waste orders of magnitude faster than bacteria could alone. Phase 3 was the chemical reset. Within 6 months, the neon orange color had vanished. The gross stage of fermentation resolved into a layer of rich, black, loamy soil. The decomposition process neutralized the initial acidity of the peels. More importantly, it flooded the soil with the nutrients that limit tropical plant growth: nitrogen, phosphorus, and potassium. The 12,000 tons of waste acted as a massive nutrient injection, paying off the soil debt incurred by decades of cattle grazing. The hardpan soil was now covered in a deep layer of aerated, nutrient-dense compost. The system was now primed for a biological software upgrade. But just as the biological mechanism was engaging, the project collided with a different kind of reality: corporate warfare. A rival juice company, Tico Fruit, viewed the deal not as innovation, but as unfair competition. They had invested heavily in conventional waste treatment infrastructure, and they resented that Del Oro had found a zero-cost solution. They launched a legal and public relations offensive. They used the ugly visuals of the project against it. They accused Del Oro of defiling a national park, and legally they had a point. The concept of industrial symbiosis had no precedent in Costa Rican law at the time. To a judge, dumping waste in a park was illegal, regardless of the scientific intent. In 1998, the Supreme Court ruled against the project. An injunction was issued. The experiment was killed. Del Oro was forced to go back to conventional waste processing, and the pilot plot was abandoned. A large yellow sign, erected to explain the science to visitors, was left standing in the desolate field. For the next 15 years, the site was largely forgotten by the scientific community. It was dismissed as a failed experiment in garbage conservation. In 2013, Timothy Truer, a graduate student at Princeton University, traveled to the conservation area to scout research locations. Daniel Jansen gave him the coordinates of the old orange peel site, suggesting he go see if anything had happened. Truer drove to the location, but he found himself confused. He drove back and forth along the dirt road, checking his GPS. The device insisted he was at the site, but the landscape described in the 1998 records, a barren, rocky pasture, was nowhere to be seen. On one side of the road was the control plot, which looked exactly like the degraded pasture he expected. On the other side, where the coordinates pointed, was a dense, impenetrable wall of vegetation. It took Truer and his team significant effort to physically hack their way into the plot with machetes. Inside, the canopy was so thick it blocked out the midday sun. After searching through the undergrowth, they eventually found the old yellow sign. It had been completely swallowed by thick vines. The forest had not just returned, it had exploded. To move beyond anecdote, the researchers established a rigorous study. They measured every tree and analyzed the soil chemistry against the untreated control plot just meters away. The data revealed that the single application of orange peels had permanently altered the ecological path of the site. The metrics were staggering. In the control plot, the dominant vegetation was still the invasive Jaragua grass, with a few scattered, fire-scarred trees. In the orange peel plot, the canopy closure was over 90%. This is the critical tipping point. By achieving 90% shade, the trees had successfully shaded out the invasive grass. With the grass gone, the fire risk dropped to near zero. Species richness had tripled. The control plot had only 8 species of plants. The treated plot had 24. Above ground biomass, the sheer weight of wood and leaves, had increased by 176%. Perhaps the clearest symbol of the transformation was a massive fig tree located in the center of the treated plot. In the nutrient-starved context of a normal dry forest, a tree of that size would typically take nearly a century to grow. Here, fueled by the orange peel steroid injection, it had reached a diameter of 3 feet in just 16 years. The orange peels had acted as a time machine, accelerating the recovery process by a factor of 5. Critically, this was not just a fluke involving oranges. Years later, researchers replicated the experiment in another part of Costa Rica using coffee pulp, the waste from coffee cherries. They applied a similar half-meter layer to a degraded pasture. The results were even faster. Within 2 years, the coffee pulp plot had 80% canopy cover, compared with 20% in the control. This proved that the mechanism is universal. If you smother the grass and spike the soil with nutrients, the forest remembers how to grow. The story of the orange apocalypse offers a profound correction to how we think about environmental engineering. We often assume that fixing the planet requires high-tech solutions, carbon capture plants, genetic modification, or complex machinery. We also have a bias towards solutions that look clean, sterile, and precise. But the most effective restoration machine in this case was Arot. It was a chaotic, smelly, fly-infested pile of garbage. The restoration did not happen because we treated the land with reverence. It happened because we overwhelmed it with waste. The implications are massive. We currently have billions of tons of agricultural waste streams, from coffee to cocoa to grains, that are treated as liabilities. At the same time, we have millions of hectares of degraded land that we are trying to reforest with expensive, high-failure planting programs. The orange apocalypse suggests we are doing it backwards. We should not be planting trees in a desert. We should be using our waste to build the soil sponge that makes the desert habitable again. The 16-year gap between the dumping and the rediscovery is a tragedy of lost time. Had the project not been sued out of existence, tens of thousands of hectares of Guanacaste could today be lush, carbon-sequestering forest. But the 3-hectare island of jungle that remains stands as proof of concept. It proves that even in the most degraded, arrested landscapes, the potential for life remains. It does not need a miracle. It just needs gravity, time, and a mountain of peels.